So let's make a start for the morning session. So welcome back to the workshop. We have two excellent speakers this morning. The first one is a familiar face to many of you, is Chiheb Ben Hammouda, and he's currently an assistant professor at Utrecht. He did his PhD at KAUST, as many as you know, and a postdoc at Aachen, and he's very well known for his work in quantitative finance and stochastic reaction networks. He's going to be speaking on empowering Fourier-based methods for computing expectations and pricing multi-asset options. So please take it away, and thank you very much for attending and giving a talk.
Thank you very much, Ajay, for the nice introduction, and thank you and Raul for inviting me to give a talk in this nice workshop. This is a joint work with Christian Baya, Michael Samet, and Antonis Papanteleon and Raul Tamponi. So let me first go through the main ideas that I want to convey throughout the talk. Of course, the main application will be about pricing multi-asset options, but you may think about the tools that or the ideas that I will convey relevant for applications where you want to efficiently compute a high-dimensional expectation of a certain function j evaluated at the terminal value of a certain process x. And the features of your problem has the following. So the PDF, or the probability density function at terminal value of your process, is either not known explicitly or expensive to sample from, G is non-smooth, and the dimension of the problem is large. So we know that in this kind of problems, Monte Carlo method is a natural way to go because it has a convergence rate that is independent of the problem's dimension and the integrand's regularity. However, in many cases, it can be very slow. On the other hand, the second option is to go with deterministic quotient methods, because you can express your expectation problem as a d-dimensional integration problem. And the problem here is that the non-smoothness of GA and the high dimensionality may deteriorate the convergence of such type of methods. So what we will see throughout the throughout the talk is that we can try to uncover what the available hidden regularity that we can have in the problem, but by mapping our original problem in the physical space to the Fourier space, provided that we have access to the characteristic function, which is basically the conjugate of the Fourier of the density function. And in that case, we will see that we can express now our original problem as a new d-dimensional integral that expressed as the product of the Fourier of the original function times the characteristic function. And the nice features of this new problem is that the Fourier of J and the characteristic function admits analytic extension to the complex plane, so they will be highly smooth. And this will be controlled by a vector of parameters that I denote here by bold R, which also shifts the contour of integration into a parallel line to the real line in the complex plane. And as we will see, there is a challenge here because there are many values of these parameters, admissible values of these parameters that we can use. However, certain values can deteriorate the regularity of our Fourier integrand. And what we propose is that we can try to optimize the choice of such parameters through a certain rule based on contour integration error estimates. Once we dealt with the smoothness issue, so once we recover a highly smooth integrand now in the Fourier space, we are set to take care of the high dimensionality, and we will see that we propose different solutions. One way is to do some sparsification and dimension-adaptivity, and the second approach is through using quasi-Monte Carlo, but as we will see, this involves some other challenges because we need to design an efficient domain transformation, because our Fourier integrand will lie in RD, and as we know, quasi-Monte Carlo points are usually sampled in the unit hypercube. So these are more or less the ideas that we will go throughout the talk. And my talk will be based on the following two references. So let's start with motivating why we do the things we do and setting up the problem. So first, let me briefly explain what is a European option. So a European option is basically a financial instrument that gives the holder the right, but not the obligation, to either buy or sell one or more underlying assets at a predetermined strike price that we denote by capital K here. And it can be exercised on a future maturity date denoted here by capital time T. Usually options are used either for hedging purposes. So basically you want to protect against risky positions in case there is a rising or declining asset prices, or also to maximize profits and limit losses. Another application is that you want to profit from betting on the relative or overall behavior of your assets, what we call usually speculation. Without distracting you with many details, we can express the problem or the task of pricing a multi-asset European option as the computation up to discount factor of the following expectation, where P here, it will be related to what we call the payoff function. And the vector x here will be related to a stochastic process representing the log prices of the underlying assets at time t. These expectation will be defined with respect to what is called the risk neutral measure. So the main idea is that the option price task will be the efficient computation of the following expectation. Now let's see the features of this problem. So of course, the first thing is to look at the structure of the payoff. And in quantitative finance, the payoff function is usually non-smooth. And here I'm showing some examples. So you can have payoff functions that have discontinuity on derivative, like the basket put option, which is given by the following illustration, or rainbow option, for instance, column mean option. Or we can have also examples of options that have payoffs that have discontinuity in the function itself, like for instance the cash or nothing option, which is expressed as a product of indicator functions. So the first thing that we see is that our integration problem or expectation problems will involve a non-smooth payoff function. The second thing that we need to set is a model for the asset prices. And what we assume here is that so the d-dimensional process here characterizing the log of assets prices will follow a certain multivariate stochastic model, and we are constrained with models where we are able to have explicit access to the characteristic function. This is because we want later on to map the problem to the Fourier space. And particular cases that particular examples that we will focus to illustrate the ideas of this talk are some kind of jump diffusion models, which are examples of Levy models. And this kind of models has exhibit a remarkable fit to empirical market behavior, because they are able to account for market jumps in prices and also heavy or semi-heavy tails that can be observed in the market. And for illustration, we will consider the variance gamma model and the normal inverse Gaussian model. And as you see here, maybe compared to what you are familiar to, which is the geometric Brownian motion, you see that this kind of processes mix diffusion and jumps. So you observe that you have some jumps in your trajectory. Now, we can see this more clearly by looking at the dynamics of such processes. So basically, the variance gamma process and the normal inverse Gaussian process can be seen as evaluating a Brownian motion with a drift that is evaluated at a random time. And the random time for the case of variance gamma is modeled through a gamma process, which is denoted by a capital J here. Or it can be modeled with inverse Gaussian process, which is the case for the normal inverse Gaussian. Okay, so now we have explained the structure of the payoff function, the models that we will consider for the option pricing task. let's go back to the problem of interest. So the problem of interest, as we explained, is in pricing multi-asset options is to compute a discounted expectation. And if we look at the different possibilities that we can use, we have here some illustrations about the different sampling methods that we can use. And for relevance here, I'm showing all the sampling methods in the unit hypercube because quasi-Monte Carlo points can only be sampled on the unit hypercube. So if we start with the Monte Carlo, so all these methods can be seen as a weighted average of evaluation of your payoff at the sampled points throughout the using the different methods. So for the case of the Monte Carlo method, we know that the weights are uniform and the points here will be sampled with respect to the density at the terminal time of your process. And one feature of this kind of sampling is that the sampling is random. You may observe that your points will cluster into a certain region and maybe miss important regions where you could have some variation of your method. And unless you use maybe important sampling or change of measure, this can result in a bad performance of the Monte Carlo method. On the other hand, we have other options which are more or less deterministic. And if we look at the quasi-Monte Carlo method, we have more structure in the sampling here. Basically, the way that the points are generated is to ensure a uniform coverage of the unit hypercube by minimizing the discrepancy between the points. So we have more structure. The weights here will be also uniform, and the points are sampled deterministically. Now we can have more structure in our sampling by using quadrature methods. For instance, for the case of tensor product quadrature, what we do, we sample with respect to one dimension following a certain quadrature formula, and then we tensorize this rule all over the dimensions to obtain the grid that we will use later on for the evaluation where we evaluate our payoff function at the different points. An alternative to the tensor product quadrature is what is called adaptive sparse grid quadrature. So the adaptive sparse grid quadrature will give now more structure to the sampling by taking into account the information from the function itself. Because as you see here, you may sample maybe more points with respect to one dimension compared to the other. I think this grid was derived for a function that depends exponentially with respect to the second dimension, and maybe quadratically with respect to the first dimension. And here we use adaptivity, and the sampling is done in a posteriori fashion compared to the tensor product quadrature, which is done a priori. So the main message with respect to the different sampling method is that we start with Monte Carlo, which has no structure in terms of sampling, and it can miss important regions in your domain with respect to the variation of your function. And then we can improve the structuring of your sampling as we go from quasi-Monte Carlo to adaptive sparse grids. Now, the main question how this can impact the convergence or the complexity of the different methods. And this is given by the following slide, which I titled as Fast Convergence when Regularity Meets Structured Sampling. So for the case of the Monte Carlo method, we did not assume any structure about our sampling, so it was random. And this gives the advantage that the rate of the convergence of the Monte Carlo does not care about the regularity of the integrand and the dimension. However, the rate of convergence is slow. So it converges as 1 over square root of m, where m, again, is the number of function evaluation that you do in your sample average. Now, by using the more structure through the quasi-Monte Carlo, we can double the convergence rate with respect to the Monte Carlo method. However, this comes with a requirement that we have control on the first mixed partial derivatives. So we require some sort of integrability of the first mixed partial derivatives of the integrand. And if we miss such kind of requirement, we can get back to the worst case convergence, which is similar to the rate observed for Monte Carlo method. Interestingly, is that for the tensor product washer, which is also using structured sampling, we can obtain exponential convergence with respect to the order of bounded total derivatives, as you see here. However, due to the tensor product architecture, the convergence rates will also deteriorate exponentially with respect to the dimension. And this thing can be alleviated through the use of adaptive sparse gauge washer, which, if we remember, now does not have structure only with respect to covering your domain, but also it takes the variation of the function into account. And in this case, we can still have exponential convergence that will be related to the exponent p, which will be linked to the order of bounded weighted mixed partial derivatives. So again, if we look at, so the main message of this slide is that if we provide enough regularity and we design our sampling in a structured way, then we can enjoy a very fast convergence rate. Otherwise, in the case of the Monte Carlo, we get a very slow convergence rate. And the nice thing with the quasi-Monte Carlo that you can observe, it has the minimal requirement with respect to the regularity, and still it can achieve a nice convergence rate because you double the convergence rate with respect to the Monte Carlo method. Now, if we go back to our setting, we don't have that luxury. So if you remember, our expectation problem involves payoff functions that are either non-smooth with respect to the derivative, so they have this continuity in the derivative, like the case of the basket put and the column mean, or they can be they can have discontinuity on the function itself. So what we need to do basically is to see if we are able to uncover the available hidden regularity, because otherwise, if you use the previous deterministic methods, you will not get good convergence rates. And there are many different ways to do this. For instance, you can do this by analytic smoothing or bias-free modification. Basically, the idea here is to take conditional expectation over a subset of integration variables. This is very relevant in many applications. However, the shortcoming here is that sometimes it's not trivial to come up with a good choice with respect to the dimensions where you want to pre-integrate with respect to. A second option is that you try to solve the discontinuity numerically. So what you can do, you try to use root finding methods to locate the discontinuities, solve them, and then you pre-integrate or integrate in the regions that are separated by those discontinuities. This is also a nice option whenever you are not able to do the explicit smoothing or mapping your problem to the Fourier space, because otherwise it can come with an extra cost. The third option, which will be basically the main, the today's talk, is to map the problem to the Fourier space. And I emphasize that this option is relevant when you have access to the characteristic function, which is the conjugate of the Fourier of your density. To motivate you further, here I show why it makes sense to map the problem to the Fourier space. So again, on the left side, you see the Fourier, the payoff function in the physical space, and you see on the right side their corresponding Fourier transform. And it's obvious that you improve the regularity when you map the problem to the Fourier space. So this can motivate us to go forward. Okay, so now we want to explain how we map the problem to the Fourier space to uncover what we call the available hidden regularity. And this is basic, and this is given by the following formula, which is given by this proposition. So under these assumptions, which I will come back to it later, we can show that our discounted expectation that we had originally is equal to this constant term times now a new integral in d dimension of the real part of the product of the characteristic function of the process times the Fourier transform of the payoff function. What you can see here also is that the integration in the Fourier space is done with respect to a parallel line to the real axis in the complex plane. And the location of that parallel line is given by this vector of parameter that we will call from now on the damping vector. And this vector is very important because this is involved in the assumptions here that ensure integrability of the Fourier of the payoffs, and they will also give us a control on the analyticity region of the integrand. So the damping parameter R here will be belonging to intersection of the strip of analyticity of the Fourier of the payoff, which basically is characterized by the following set. So here, this set ensures that you control the growth of the payoff function in the physical space. And also you have the L1 integrability in some location on the in the complex plane of your Fourier payoff. And the second condition, make sure that your characteristic function is bounded intuitively. This makes sure that your characteristic function does not have singularities on those regions that are shifted by the damping parameter in the complex plane. So this mapping is very interesting because it's very modular, right? So what it tells you basically is that starting from the original problem where we have this expectation of the non-smooth payoff P of your process at terminal time, give me the characteristic function, which is the conjugate Fourier of your density, give me the Fourier of your payoff function, and then now it's casted into the dimensional integration problem, and then I can use maybe the numerical tools that we have for efficiently integrate this d-dimensional integral. Just a brief mentioning of the proof, which is not complicated. So here we started with the discounted expectation and the physical space. What we use first is what is called the inverse generalized Fourier transform. So maybe you are familiar with the usual inverse Fourier transform, which basically does the inverse of the Fourier transform for the Fourier payoff, which is only evaluated at the real line. But here, maybe I need to mention again that these characteristic function and the Fourier payoff are extended once to the complex plane. So they are evaluated also, they are evaluated in the complex plane. So that's why here we use what is called the inverse generalized Fourier transform to first express the original payoff function with respect to its extended Fourier transform. And then once we interchange the expectation and the integral using Fourier theorem, then we end up with the following expectation, which is nothing else than the characteristic function evaluated at y, shifted with respect to the real line with this damping parameter R. And then we obtain our formula, and you see here where the assumptions are coming from. So in the first transition here, we needed to assume the integrability, the L1 integrability of our Fourier payoff in this region of the complex plane. And then here we needed to assume that the characteristic function is bounded to use Fourier theorem, and this will give rise to the analyticity strip of our damping parameter, so it should belong to the intersection of those two regions. In terms of notation, so from now on, we will call now the integrand that appear in our integration problem as J. So J here would be evaluated in RD. R is the vector of damping parameter that will be belonging to the strip of analyticity. And of course, we will have dependence with respect to the model parameter throughout model parameters throughout the characteristic function, and also the payoff parameters throughout the Fourier payoff. So this will be the integrand that we will use from now on in the Fourier space. Yeah, so far I just mentioned the abstract formulation that enables us to map the problem from the physical space to the Fourier space. So let's see some examples of the characteristic function and the Fourier payoff. So here I'm showing some examples relating to the geometric Brownian motion, the variance gamma, and normal inverse Gaussian. And also I relate to how the strip of analyticity looks like for each model. So of course, for the geometric Brownian motion, we have, so the dependence will be we're having something like a Gaussian with respect to the complex variable. And then this leads us to the fact that the strip of analyticity will be the whole RD. However, this is not the case for the variance gamma and normal inverse Gaussian, because you could have singularities because of the structure of the characteristic function. And that's why the strip of analyticity of the characteristic function is more complicated. And as I mentioned here, this strip of analyticity will depend on the model parameters for each model. So without going too much in detail, so here you see the dependence with respect to the variance gamma parameters. Here, the dependence with respect to the normal inverse Gaussian. Now, how they look like, let's say geometrically, you can, for instance, look at the normal inverse Gaussian. And if you take the matrix delta here as identity, you can see that basically in RD, this will look like a ball or open ball that is centered around beta, vector beta, and has a radius which is equal to alpha. We'll see a visual illustration later on, but this is something that you can see. And it's obvious also, it's not trivial to maybe solve this problem and know this complex region of the damping parameters, which ensures the analyticity of the characteristic function. The story is more simple. Simpler for the Fourier of the payoff. So here again, I show the scale payoff and the corresponding Fourier, and how the analyticity strip looks like. So as I said, it's simpler for the case of the Fourier payoff. For instance, for the basket put, it will be the right half planes, so the intersection of right half planes in RD, and for the column mean, it will be restricted left half plane in RD. Yeah, here we have less complication because also it does not depend on many parameters like for the characteristic function, because it involves the model parameters. Now, to make things maybe more concrete, let's look at a certain visualization. So here I'm showing the strip of analyticity for the case of two-dimensional column mean option under the variance gamma model with using different parameters. So as I said, the delta x, which is the analyticity strip of the characteristic function, will look like a ball in RD. So here you see that you have the following shape with respect to this parameter, and this is the case where you have anisotropy with respect to the sigma. So you see the following shape, and then it intersects the strip of analyticity of the Fourier of the payoff. And the delta V here will be basically the analyticity strip or admissible values of the damping parameters that we can use to express our integrand, and which is the condition basically to make this formulation viable. So the first observation is that the strip of analyticity highly depends on the model parameters, and a natural question, as we see here, maybe in 2D, as we go higher in dimensions, there will be several possible choices for the damping parameters. So how do these choices impact the Fourier integrand that we expressed before? And this is maybe a motivation that give you maybe a partial answer about such an effect. So here we try to show different possible values of the damping parameter in R2 for the case of a two-dimensional basket put option under variance gamma model with these parameters. So what you see that there are certain values of the damping parameter that produces a Fourier integrand that is well behaved. So if later on you apply deterministic quadrature methods, you expect that they will be very efficient. However, if you shift either below or up with respect to those values, you can see that now you can start observing the integrands having maybe oscillations and also high peaks. These two features are not, of course, good when we do numerical integrations. So the main message with respect to this illustration is that it really matters to choose carefully the values of the damping parameters. First, because we have many possible values that we can end up with. And second, because they impact, so if we don't choose them carefully, they will impact the regularity of our integrand. So again, so this is the challenge. The second challenge that we try to address, how to choose this damping parameter carefully. The interesting thing is that in the literature, there was no precise analysis on the effect of such parameters on the performance of numerical quadrature methods in the Fourier space, and also no guidance on how to choose them to maybe speed up convergence. And what we propose is that we design a generic optimization rule for choosing such parameters that are based on contour integration error estimates. And this is what we will see in the following section. And this is what I call parametric smoothing. All right. So how we will choose such kind of parameters? Again, we want to speed up convergence of quadrature methods, and the natural way to go is to look at error estimates or quadrature error estimates. And in this case, we can have maybe two representations. So the first one relies on expressing the error estimates using high order derivative of our integrand that is highly smooth. However, the shortcoming of such representation is that high order derivatives are usually challenging to estimate and control, and this will result in a complex rule for optimally choosing the damping parameter. So we do not want to make such a choice complex. The second way to go is to use another representation, which is based on contour integration, that is based on Cauchy integral theorem in the complex plane. And this is valid for functions that can be extended holomorphically or analytically into the complex plane, which is basically our case, right? So when we map the problem to the Fourier space, we ensure that our integrand can be extended analytically into the region which we denoted by delta V of those damping parameters. So our integrand fulfills such kind of condition. And as you will see, this will result in a much simpler rule for choosing these damping parameters. How we do this? Yeah, so this is through, as I said, error estimates based on contour integration. And what it tells you is that if you have a function f that can be extended analytically along a sizable contour that we denoted here by calligraphic C that contains the support of integration, then we can show that the quadrature error, so here we are denoting the quadrature error, can be bounded by, let's say, contribution of two terms. The first one is the supremum of our function in the complex plane, so over all possible values belonging to the contour of integration. And the second term involves a contour integral of a function that is basically related to the quadrature rule that you are using. So this is the error estimates that you can show for functions that can be extended analytically into the complex plane. And yeah, in our work, I'm here for illustration. I show the 1D estimate, but also you can show that this can be extended also to the multivariate setting, which we are interested in. The nice thing with also this estimate is that the first term does not depend on the quadrature rule. So it basically depends on the function that we want to integrate in the Fourier space and the choice of the contour. And remember that the choice of the contour in our setting, it basically relates to the damping parameter, because these parameters are the ones that shifts the integration contour to a parallel line to the real axis with those values. So how we can use such kind of error estimates to derive a damping rule? So again, just we use this error bound. So what we propose is that we can choose our damping parameter such that we minimize over all possible values of those parameters in the analyticity region, which is delta V, so all admissible values of the damping parameter of the supremum of our function, our integrand, which I recall here in the Fourier space, given the model and the pair of parameters. So this can give us what we call optimal values of the damping parameter that can speed up the convergence of the quadrature. And interestingly enough, we show that maybe, so at the beginning, this problem looks like maybe very complex. So using certain properties in the Fourier space, we can show that this is reduced to minimizing over all possible values of damping parameter the integrand G evaluated at the origin. And then, of course, this is much simpler optimization problem, but still we cannot solve it analytically. So you need to use maybe some kind of optimization methods, for instance, trust region method. So we started with the error estimate based on contour integration. Then, inspired by that, we derived a rule to choose the damping parameter, and the question, does it let's say produce the desired let's say behavior. So here first I will show 1D illustration, but later on we will see maybe more examples with convergence rates in high dimensions. So through this plot, I want to show you the relation between the integrand, which is our Fourier integrand here, which is G, and the convergence of 1D quadrature rule here, the Gauss-Laguerre quadrature. And as you see, so here I'm showing different choices of the damping parameter. And here the red one will correspond to the one based on our rule. And you see first that the one that is based on our rule that minimizes the peak around the origin will produce a convergence rate that is the faster and also with, let's say, lower constant compared to the others. And also what you observe is that for choices which have maybe higher peaks around the origins, this is also related to the worst performance in terms of numerical convergence of the quadrature here in 1D. Okay, so this maybe gives us a motivation that the rule is working. So now coming back to our problem, what we have done so far is we started from the physical space with the non-smooth d-dimensional integration problem. We mapped the problem to the Fourier space, and then we derived a rule to choose the damping parameter which control the analyticity region of the integrand and the Fourier space. This will result in a highly smooth d-dimensional still integration problem. So the next point is how to deal with the dimension or the high dimensionality of the problem. And before going to that, I need to mention that there were also other alternative Fourier pricing methods. However, they were only efficient for only 1D and 2D problems, either because you cannot extend them to higher dimension, or because if you extend them to high dimension, they face the curse of dimensionality. And in our setting, also, we if we apply after maybe we get the highly smooth integral, and if we apply naively tensor product quadrature, then what we see and what is expected also is that the convergence will deteriorate exponentially with respect to the dimension of the problem, which is in our case the number of underlying assets. So this is just an illustration of a problem where we try to price a column mean option under normal inverse Gaussian model with respect to different dimensions for a desired error tolerance, relative error tolerance of 1%. And you see that the cost increases exponentially with respect to the dimension. So the question how we can deal effectively with this issue, the first way is to try to do some sparsification and dimension adaptivity techniques to accelerate convergence through using adaptive sparse grids. We will go briefly through this first option. And later on, we will focus more on quasi-Monte Carlo, which enables us to push the performance of such kind of methods to higher dimension. But in that case, we need to take care of transforming the domain, because as I said earlier, quasi-Monte Carlo points, sample points, and the unit hypercube, but the integrand or the Fourier integrand that we are interested in lies in RD. So without going too much in detail here, I'm more or less reminding the picture that we saw in the introductory section. So this is how the grid will look like in the tensor product. So you sample with respect to one dimension, and then you tensorize your rule all over the dimensions. Of course, you can apply maybe L1 norm with respect to the indices of your quadrature points, and then this results in sparse grids. So you have a sparsity in your grid. And you can even have more structure that takes into account the variation of your function. So this is the thing that I showed you earlier. So here you have this function, for instance, that depends exponentially with the second dimension and quadratically with the first dimension. So it makes sense to sample more with respect to the second dimension to follow the variation of your method compared to the first dimension. Yeah, so this is the difference between the different methods. So here we, in the first option, we'll use adaptive sparse grids. And by this plot, I show the effect of choosing the damping parameter on the performance of the adaptive sparse grids for the two examples. So the 4-dimensional geometric basket put option and the 4-dimensional variance column mean. So the red plot or the red curve will be related to the one that is related to the optimal choice following our route. And the other ones are more or less shifted location with respect to that optimal choice. And it's obvious, right, to see that, for instance, in this case, to achieve a relative error tolerance below 1%, you will require maybe a factor of less than 10 times or even hundreds of times than the ones if you use other choices of the damping parameter. So this was consistent for different examples and for different dimensions. So we see obviously that the damping rule is not only valid for the 1D illustration that I showed you, but also it's still valid for high dimensional problems. We also compared to the Monte Carlo methods for different sets of dimensions and pair of functions and models. And you see that up to 6 dimensions to get a relative error below 1%, for the basket put option, we could have our method so that combines adaptive sparse grids with optimal damping 10 times faster than the Monte Carlo in the physical space. And for column mean, we could even have 100 times faster than the Monte Carlo method. With the adaptive sparse grids, we could go to a certain dimension that is around 7 and 8. And the natural question was, can we design a better method that can help us to push the performance of the Fourier-based methods to a higher dimension? And this will be illustrated through the use of the quasi-Monte Carlo method. All right. So again, I recall our Fourier integrand, which lies in RD. And as we know, quasi-Monte Carlo constructions are restricted to the unit hypercube. So obviously, we need to do some transformation on the integration domain to be able to use quasi-Monte Carlo points. And maybe the natural transformation is to use a certain inverse of the cumulative distribution function. So then we can show that we end up now with a new problem that lies on the d-dimensional unit hypercube of the following. So in the numerator, we have the composition of our Fourier integrand with the inverse of the cumulative distribution functions. And due to the change of variables, we will have this term appearing, which is the composition of the corresponding probability density function and the inverse of the cumulative distribution function. Of course, here we put certain dependence because first, this will depend on the choice of the family of the probability density function, but also the parameters within that family. Now, let's say before going through how to choose such a transformation, once we have chosen the inverse CDF and of course the corresponding PDF, then we are able to just use the standard construction of the quasi-Monte Carlo and even the randomized quasi-Monte Carlo, which is given by the this double average, where here so these points basically are obtained by a certain randomization of the deterministic sequence of the quasi-Monte Carlo points. For instance, you can think about randomizing those points using random shifts, where the random shifts here are independent and identically distributed with uniform distribution in the d-dimensional unit hypercube. So before going to how to choose the inverse CDF, so once we map our problem, then we are able now to use the quasi-Monte Carlo method. But still, it remains how to choose such transformation. And here I'm trying to motivate that you really need to carefully choose such transformation. Why? Because if we look now at our new Fourier integrand, after we do the transformation, we will have appearing in the numerator a term that will decay to 0 as we approach the boundaries. So this is clear, right? If you take u to the 0 and 1, and here you have the inverse CDF, then the numerator will go to 0. So unless you ensure that your numerator decays faster than your denominator, then naturally you can end up with singularity near the boundaries. And looking at the theory of quasi-Monte Carlo, this is not a good thing because the error estimates are based on bounded on function with bounded variations. So of course this will deteriorate the quasi-Monte Carlo convergence. And this is also illustrated with respect using this plot. So this is our original Fourier integrand without doing any transformation. This is for the case of the call option and the geometric Brownian motion. And this is the transformed one. Here we use the Gaussian density with the scale parameter sigma tilde. And obviously there are choices, for instance, the blue ones that can lead to an integrand that has a blow up in the corners with respect to the boundaries of the unit hypercube. So this leads us to the question how to choose the density, which is related to the inverse CDF that we will do the transformation with, and also how to choose its parameter. So there are two questions that we try to answer. And if you look at the literature, there were some works that consider such kind of transformation to avoid singularities for the quasi-Monte Carlo, but they consider different settings. What I mean by different setting, first, they consider transformation for a weighted integration problem. So you have a certain density of your integration problem, something that we don't have. So our Fourier transformed Fourier integrand now does not have any weight. The second thing is they provided such kind of transformation in the physical space. In our case, we have the transformation in the Fourier space. And the third thing, they always assume certain dependent structure to facilitate such transformation, because then you can decouple the choice with respect to the different dimension. This is another thing that we also relax, and we try to provide a rule that takes into account the dependent structure between the dimension. And in the case of option pricing, it takes into account a correlation between asset prices. Okay, so so what we propose in our setting, so we propose design a transformation of the Fourier integrand that is adapted to our setting. How we do this? So so if we look at our problem, so this is again recalling this is our transformed Fourier integrand. And if we expand our original Fourier integrand, if you remember, this was the product of the characteristic function and the Fourier of the payoff. So if we expand it, then this will result basically with the following expression. And what we use to design the transformation is the fact that we will have the decay of the characteristic function much faster than the decay of the Fourier payoff. This is using a property that is well known for Fourier transform, which exchanges smoothness into decay. So we know that the payoff functions, as I showed earlier, are less smooth than the densities of the pricing models. So then what is expected is that they will have a slower decay in the Fourier space. And for this reason, what we to design a simpler rule, it's enough to concentrate on this term, because if we are able to ensure that we have a fast decay of the numerator and with respect to the term involving characteristic function of this quantity, then this quantity will only help to have a much better behaved integral. So the design of transformation will be to control the growth at the boundary terms of the following ratio, which is the composition of the characteristic function with the inverse CDF over the PDF composed with the inverse CDF. So let me see how much time I have. Okay. So how much time I have, AJ? Because we started 5 minutes late.
Yeah, sorry, so yeah, so we've got about 10 minutes, including questions. So,
okay,
so if you could finish it.
Okay, I'll try to speed up in 5 minutes. Okay, so
okay, thank you.
Yeah, so so again, the aim is to so the first thing, we need to choose the family of distribution functions, and as I said, so we try to control this decay. And if we look now at the characteristic function, we can see that we can choose our the family of the PDF to follow asymptotically the same functional form of the characteristic function. For instance, for the geometric Brownian motion, we see that we have this Gaussian shape for the characteristic function, so we can use our family of transformation based on Gaussian densities. Here we have a polynomial decay in the characteristic function, so this leads us to choose our PDF in the family of generalized student distribution. For the normal inverse Gaussian, we have a root exponential form, and then this leads us to choose Laplace PDF. So the first thing is to choose the family of the PDF, which will enable us to derive explicit conditions, because then we can link now the parameters of the PDF for the transformation with respect to the characteristic function. And by doing some computations for the terms at the boundaries, we were able to show growth conditions that enables us to have a well-behaved integrand that relates here the purple parameters, which are related to the transformation, so the PDF of the transformation, with respect to the blue parameters, which are related to the characteristic function. So we have conditions that if fulfilled, then we avoid to have the singularities at the corner. So the limiting case will produce a constant at the boundaries, and then the decay of the Fourier transform of the payoff will still enable us to have a decay of the integrand at the corners. Otherwise, you can enable faster decay if you go beyond the limit. And yeah, through these plots, we show that, for instance, this was for the Vance gamma, and the blue one was the one that is fulfilling the condition. And as you see, if you look at the convergence rate of the quasi-Monte Carlo method, you see that you achieve much faster rate compared to other choices, and also much better constant. The same thing was for the normal inverse Gaussian. So definitely you see the effect. This is a 1D to show the link with respect to the integrand. Maybe I need to skip this, but also the correlation is important. So we also derive the rules that takes into account the correlation structure. This gives rise to another challenge on how to evaluate efficiently the inverse CDF. because of course now compared to the case of the independent case, you cannot write your inverse CDF as a vector of the univariate inverse CDF with respect component wise. So we needed to have some tricks based basically on Cholesky decomposition and choosing the family of the PDF following a certain normal mean variance mixed distribution. And then, of course, this changed a little bit the problem. So you can see maybe more details in the paper. And also, we were able to derive maybe now more maybe complex condition compared to the independent case, because you cannot decouple the dimensions, but still we were able to derive nice conditions that gives us control on the behavior of the integrand on the corners, and then this leads to much better convergence of the quasi-Monte Carlo, as you see here. So this is the case of two-dimensional call under geometric Brownian motion. So you see, if you take now the rule, you obtain much better behaves compared to the case where you don't take into account the rule that we derived here. If you compare to the Monte Carlo, this is a 6D problem for the variance gamma and the normal inverse Gaussian. And as you see, we recover. So this is the tolerance, so the complexity plot. And since now we double the convergence rate, if you remember, provided that we have control on the smoothness of the integrand, and this is why we did the transformation. So we recover now a double complexity rate of the quasi-Monte Carlo compared. So we have a tall -1 compared to tall -2 for the Monte Carlo. So this is a big improvement in terms of rate. And I finish by this nice plot where we try to compare the performance of the tensor product in the Fourier space, which are given by the red curves, the Monte Carlo method in the physical space, and the randomized quasi-Monte Carlo in the Fourier space, using also the optimal damping rule and the domain transformation that we designed. And this is with respect to different dimensions up to 15 dimensions for the column mean under the normal inverse Gaussian and the variance gamma model. And what you see here, this is what was expected for the tensor product. So we have exponential dependence. So the complexity deteriorates exponentially with respect to the dimension. But what is nice is that we keep advantage of the quasi-Monte Carlo in the Fourier space compared to the Monte Carlo method up to 15 dimensions, and with a factor that is equal to 100 in terms of CPU time. And what is nice here, I mean, we expect that the Monte Carlo complexity does not depend on, let's say, on dimension, but this is always in terms of rate, right? But so this dependence that you see here conveys that the constant, the dependence of the constant that is in front of the rate in the Monte Carlo method. So obviously this depends on the dimension, and that's why we still see advantage of applying quasi-Monte Carlo in the Fourier space using our domain transformation and optimal damping for such kind of task up to 15 dimensions. So maybe I skip the conclusions. So then if you want to look for more details, you are welcome to look at the following two references, and these references are related to other ways on how to smooth the problem by either numerical smoothing or bias-free modification. And finally, also you can check our method with this repository, which was nicely put by Michael. So then you can check, I mean, the results that were conveyed through the talk and also in the papers. By that, I thank you for your attention.
Thank you for the talk, a very nice talk. Do we have some questions from the audience? Can we hand the cube to Alex, please?
You can do that. Hi, hello, thank you. Can you hear me?
Yes.
Hi, so just a quick question. I mean, you need the characteristic function to do these things, right? For the model. That's yes. Somehow the starting point.
Yes.
And I was wondering whether it would be possible to generalize any of these to, say, a fine model. So you have some stochastic volatility with jumps.
Yes.
Where the characteristics are also, I know you use the properties of the density sometimes, but in general, that would also be very interesting and I think largely unexplored.
Yeah, that's a very relevant question. Actually, at the moment we experimented only jump diffusion models, but of course, like if you look at stochastic volatility models like Heston model, even rough stochastic models like rough Heston model, you are able to derive the characteristic function, maybe not in closed form because you need either to solve Riccati equations or the fractional Riccati equation, but still, as I said, either you have explicit access to the characteristic function, but even if it's semi-analytically, then you can still apply the same machinery that we provide through this approach. So still, this approach can be extended to stochastic volatility models, provided that you are able to derive either explicitly or semi-explicitly the characteristic function. Does this
yes, I think you could also include jumps. You could include
Yes,
jumps
yes.
also, right?
Of course, yes, we could. Yes, of course, you can
Join jumps with volatility and the spot also, right?
Indeed, yes.
We have time for one more if anyone else wants to ask something. Yes.
Yes, okay. Come. Ready?
Hello. Hi, Chiheb. This is Shyam here. Nice to see you again. Thanks for the nice talk. Yeah, I had a question to do with, to do with the case when, for example, if the strike price maybe is far away from the stock price at time t, then how would this translate to the Fourier? How would this translate to the Fourier space? And do you need some extra important sampling on top of this? And in that case, do you think it can be included in this machinery?
That's actually a nice question. I mean, if you look at the domain transformation, for instance, the quasi-Monte Carlo, it's kind of if you can look at it in the stochastic case, it's kind of change of measure or importance sampling. But there we did not care about the strike, but we cared about the singularities, right? And for the singularities, maybe for the strike, it's less maybe impactful in the deterministic quadrature. Why? Because the problem with Monte Carlo, as I said, is that when you sample your points, you don't care about the behavior of your function. So the problem is that if you care only about the density, you can sample more points in certain region, and you miss regions where you still have to follow your pair function, right? I mean, because of you are out of the money or into the money. If you map to the Fourier transform, or I mean, even if you go to the quadrature, this problem can still have an impact, but it's less because especially if you try to design your quadrature to take into account, for instance, the information of your function, like if you use adaptive sparse grids. But if you want also, you can also do kind of domain transformations. I mean, if you want to call them important sampling, but in deterministic case, maybe better to call them as domain transformation. But at least what we observed, you have less impact, I mean, on such kind of issues. And we also show, I think, some examples in the first paper where you have out of the money, and of course, Monte Carlo will suffer more for those cases. Does it answer your question?
Okay, yeah, thanks. Yes, thanks, Chiheb.
Okay, so let's conclude the talk now. Thank you so much again for your talk, Chiheb.
Thank you, Ajay. Thank you very much.
Thank you. So we'll just change over and put Eric's talk on the computer. Just give us a few moments.